Good afternoon, students. We're now with lecture, what are we, 11, but actually this is, I usually combine lectures 11 and 12. Chapter 9.3, phases that we're going to look at now, is quite a lengthy section, and then chapter 9.4 is rather short. But I think since we're doing this in video now, what I'm going to try and do is let's do the whole 9.3 on phases. And then at the end we'll just add that little bit of 9.4. So this might end up to be quite a long lecture. I'll see how I go for time. Okay, what we need to keep in mind, why are we busy with now phases? What is a phasor? In chapter 9.2 we just looked at sinusoid. So there we stayed in, let me just put this there, in the time domain. 9.3 moves us from a time domain into a frequency domain. Now that might sound a bit freaky, but you're going to see where this leads to. Where do we want to end up? By the end of chapter 9, what we want to be able to do is to convert our inductors and capacitors, which is now connected in an AC circuit, into an equivalent resistance or resistive type of element, so that we can solve our circuit just using the methods that you've done in EBN. And remember, if you're not that clued up with EBN, that lacquer anymore, then just go and watch the revision videos that I made. So our end objective is to take what we're going to do today and what we're going to learn with phases and apply it to inductors and capacitors inside of an AC circuit, so that we can solve it using KVL, KCL, nodal analysis, mesh current analysis, Kirchhoff's laws, yeah, all those things that we're actually going to revise in the next chapter, chapter 10. So those who are a bit more mathematically inclined, or that likes that the maths behind things, you're probably going to enjoy this lecture a bit more. But again, what you're going to do, the background is actually important. Because if you understand what we're doing today, then you'll have the insight to realize what we're actually busy with when we're solving AC circuits. Okay, so what is a phasor? The textbook gives you a nice definition there on page 374. A phasor is a complex number that represents the amplitude and phase of a sinusoid. Now, I don't exactly agree with that little sentence there, the amplitude. You'll see what I mean when we get to power and AC circuits, but for now let's stick with amplitude and phase. Later on we're going to substitute the amplitude with RMS, but I'll mention that just now. So I know you did complex numbers already in calculus, and I can still remember that first lecture, which is now, where are we now? Wow, many moons, almost a quarter of a century ago, when I sat in my first year class and I saw this revelation of a complex number system. It just opens up a whole new world. So what is a complex number? So we're going to try and keep this simple, so I don't want to overcomplicate things as we just revise complex numbers. So let's just try and keep it simple and straightforward. So you can write a complex number in a number of different ways. So the first way that we can write it, z equals x plus jy. So that, if you remember, let's just call that, this is in rectangular form. Rectangular form. And you've got your real component, and of course you have your imaginary component. So that's straight enough. Then you can also write it in another format. The textbook writes it as a, I'm not going to put that version, no, I'm just going to just put this one first. In a z, the magnitude of z with an angle phi. So what is this z? So we know this is called, this is now dust-free chalk, but this dust-free chalk doesn't want to write. This is in a polar form. But then how do we get that z? So let's just perhaps say that magnitude of z, that's just Pythagoras, hey? So that's going to be x squared plus y squared and the square root. That gives you that z, and that's your polar form for a complex number. My phone is on. Let me just make that thing go shush. There we go. Polar form. Okay, then the third way that you can write this is in a exponential form. And that we're going to write as, let's keep it a bit different to what the textbook is doing, but you're going to see now what I mean there. The textbook, uses a phi, hey. So the textbook uses an R there, so I'm just perhaps going to write this as R. You'll see just now where the R comes from. And so this is your exponential form. Now, if we draw this on an axis system, no, Werner, just leave yourself a bit of space there. Okay, so assuming your x and y is positive, so if we bring this down and that across, so this will be our x, that'll be your y value, and then the length of this vector, that's the r component, and then of course you've got your phi over here. So now you've got it on an axis system. Now from this we can see that there's actually another way in which we can write this. If we expand actually from Euler's theorem, which is this one, we can also write this as r times cos phi plus j sine of phi. In other words, we take the length of this vector, cosine gives me the x part, and sine of that angle gives me that length in the triangle, which is the y component. So you've got 4 different ways in which you can write a complex number. And depending on the type of calculation that we're going to do, you're going to need a different one. So perhaps from this, everything I'm mentioning now, you can actually get from the textbook as well. Hey? Let's just rewrite this one perhaps a little bit different. Now let's write it as r cos phi plus r sine phi, but I'm just going to put the j here. So now we can see that you've got this is your x component and that there is your y component. Okay, so that's there. The r we've sorted out. I'm going to sneeze again. So we've got an equation for the z, or the r is x squared plus y squared. But what about phi? How can we calculate the angle now in terms of r and x? So the phi component, let's just write here, perhaps where r that we've got there is our x squared plus y squared. This chalk is definitely less dusty than the other ones that I had. And you've got phi is then, remember it's the, I can never remember again the English word, it's the teenoorstaande sy, the side of the triangle that's opposite of the angle. Let me know what that name is. Okay, so phi equals then a tan or tan minus 1 of y over x. So that's just a bit of trigonometry in order to calculate those values. So different ways in which we can write all these complex numbers. Let's quickly go to the textbook and let's just look at, depending on what type of calculation you need to do, multiply, add, subtract, what form of all these complex numbers do you want to use. So that is on page, let's go and look. So we are at the bottom of page 375. So there they've got let's assume you've got 2 different complex numbers, Z1 and Z2. We've got the rectangular form and polar form, and those are the 2 forms that we're going to play with the whole time. If you want to add them, you want to do it in rectangular form. So you add the real parts. Let me just, click there. I want the little hand thingy. There we go. Let's zoom in. So if you want to add them, you're going to use the real parts. And if you're going to add the real parts, add the imaginary parts, and then you can get the total. If you want to subtract, also the rectangular form. move. If you want to multiply, all right, now if you want to multiply, you want to use polar form, so you multiply the coefficients and you add the angles. Now, where does that come from? This actually comes from, if you look at this in terms of Euler's theorem or the exponential form. So remember, when you multiply exponents, you multiply the coefficients, but the exponent part that you add together. So the angles add when you divide the coefficients, subtract the angles. Reciprocal, that we're going to use quite often. So remember, there's just 1 over, and what you're busy doing here is to say 0 degrees minus the second one. So you've got one angle 0 degrees at the top and some complex number at the bottom, so it's the minus phi. Square root, complex conjugate. Now there's something that's going to become very important when we're going to do power in AC circuits a bit later on. When you take the conjugate of a complex number, all that you're doing is you're changing the plus into a minus over there. All right, and then the angle, if it's in polar form, you're basically changing the sign of the angle. And then if you take the inverse, but that's also basic. If you take the inverse of a complex number, 1 over j, it becomes minus j. All right, so that's just the basic principles. We're going to do a couple of examples now on this. Next that I want to talk about is a bit on this section, the idea of phasor representation based on Euler's identity. I'm just going to go back to the board quickly. So Euler's identity says that the exponent of a complex number can be split into a cos phi plus a j sine of phi. So yes, we still have a complex number, the real and the imaginary part. Now let's apply this to our time domain. So remember, in this section we're going to move from the time domain into the frequency domain. So this is what we're going to see. How does that happen? Is with Euler's theorem. How do we move from time to frequency domain? Now we've got a voltage in our system, in our AC system, some amplitude. Remember, it's a time function, so it's the amplitude. Cos omega t, so we're running at some frequency 2 pi f, the omega, and we've got a phase shift phi. But now this is real. I mean, if you've been shocked before in 230 volts or something, you know it's real. This voltage exists. So the cosine is only the real part of a complex number. So we're going to write this as the real part of Vm. So the amplitude stays E, and then whatever is this whole part in the bracket now comes as j omega t plus phi. So if we were to write this out as, I need a little krulakje there, as the whole Euler's theorem, it would be the real part. In this step, the textbook does not give you. You'd have Vm cos omega t plus phi, because remember, whatever's in front of this j, the phi, comes with the cosine, but then also the Vm part still needs to be there as well. Vm sine omega t plus phi. But now, only the real part of this, is the actual voltage that we're looking at. Okay, so that's a bit of a long in-between step. I actually want to now jump from this one, and we're going to rewrite this, and we're going to break up this exponential into two parts. So we keep the real part of Vm e to the j omega t e to the j phi. Right, so remember it's exponential. Sorry, that phi is not that lekker, hey? So we've just, where they've added, we've just broken it up so that where we multiply. And then I'm going to reshuffle this. We're going to combine and put these two together. Right, the real part of Vm, and then Ej, the flux, and then Ej omega t. So we haven't changed anything. We've just broken it up. But now this is where we move into the frequency domain. This part over here, these two bits, now gets defined as a phasor. So if we rewrite this in that sense, our time signal is now the real part of V e to the j omega t. Right. So then it's a little bit simplified in that sense, where, perhaps let's write this, where that V equals Vm e to the j phi. Okay. But now from what we did earlier, we know that if you've got E equals j phi, this is just Vm 1, if we take it in terms of Euler's theorem and the way we can write complex numbers, 1 times angle phi. So let's just drop the 1 there, and all you're adding there is an angle phi. So now we're back to a polar form of the complex number. So here we've got the exponential form for that complex number. Here we've got a polar form for that complex number. Okay. If we're going to draw this, oh, I put a little extra line in here. Yeah, I want to, this same thing, I'm out of space a little bit here. So now remember we can write this V now as Vm. Let's put a, did I write it as both? Yeah, like this, cos phi plus j sine of phi. All right. Now remember this, we're not saying, maybe we should put this very clear, V of t does not equal V. This is the time domain. V is now our phasor representation of V of t. I'm going to say that again. This V is the phasor representation of the time function. They're not the same thing. For one, in your time function, there's a time component. In this V part, there's the amplitude, there's the phase component, so amplitude and phase, no time component. So it's independent of time, the phasor. So that's a very important little bit of info there. Let's quickly draw that on a axis, this whole thing. So if you were to draw this, I would have liked to have drawn this now at the bottom. So perhaps you can draw what I'm going to draw now just below this. On a normal axis system. So you'd have Vm pointing, V is some phasor or vector pointing in what direction. There's your angle phi. And I put a, yeah, so this is your real axis, and here you've got your imaginary axis, and the length of this vector is now Vm. So that's just a simple scalar. Vm, the amplitude of, at this stage, the amplitude of our phasor is just a scalar, and we've got the angle phi there. And we should probably draw it like this. We've now spoken about what this part is. That's our phasor representation. It has the amplitude, it has the phase shift. What does this part now do? This e to the j omega t that we've just kind of dumped. What does this do with respect to our phasor diagram? Well, let's quickly go and have a look. But I think for that, I'm just going to clear a little bit of this. The question that we're looking at is, what does the e to the j omega t do? So the equation that we had is that v of t is the real part of Vm e to the j phi, and then that e to the j omega t. Now we've sorted out that this part is our phasor part that we can draw on a phasor diagram. What does this little bit over here do? So let's write this then as I'm just going to now focus on this section. All right, so what is this? I'm going to drop the real for now. So let's write it, this part, as V, the phasor representation, times e to the j omega t. That we can do. Then we expand, I'm going to expand this one over here, and we can say it's V. I just want to keep, why did I write the Vm there? Heck knows why. Okay, anyway, cos omega t plus j sine omega t. So I've just applied Euler's theorem to just this little part and wrote it into its real part and its imaginary part. So we've got that complex number. Now we're going to look at, let's just convert our rectangular form into a polar form to make this a little bit easier. So that then equals V times 1, because the coefficient here is just 1, and then angle omega t. So what are we busy doing? We've got this phasor, the V, multiplying it with a second phasor that has a amplitude or magnitude of 1 at an angle of omega t. But now you can see something happening, hey, where this phi over here, that doesn't change with time, but this phasor, in other words, this phasor, now the V, that angle doesn't change with time, so it's fixed. It's sitting over there. But this one is going to change with time. How? So let's write it one more step. It's V times angle. So the 1, you can drop that 1. Omega is 2 pi over the period times t. All right. So depending on what my time is, it's going to be a specific angle. So let's go and look at what happens at a couple of time periods. I want to write this one more step, sorry. But I'm going to simplify this now, otherwise I'm not going to have space below. But let's write it here first. So this is then Vm, the length of that phasor, angle. What is the angle of this V? Oh, it's phi. Great. It's phi. I'm multiplying these two, so it's plus that angle. 2 pi over t times small t. I'm going to just say that again. So we're multiplying two complex numbers. It's Vm, which is the magnitude of phasor V, that one. The angle of V is phi. I multiply that with a second phasor that has an angle of omega t, and when I multiply two complex numbers, I add the angles. So I add flux. We'll get to flux. We add phi to the angle of my second one. So this is going to determine or give me a new angle. And now the awake ones will already see what's happening. So I'm just going to shift this whole thing to the top of the board quickly. So let's look at t equals 0. What happens? T equals 0, so this term becomes 0. So you're just left with Vm angle phi. Well, lo and behold, that's what you've got over there, isn't it? Okay. So at time 0, this is what I get. So this is actually a big hoo-ha. Your phasor representation of your time function, the v of t equals Vm cos omega t plus phi. Your phasor representation, our v vector, is a snapshot of that representation at time 0. It's a snapshot of your time function in the phasor domain at time 0. What happens at time, what did I do for time a quarter? T over 4. Well, you're still going to get Vm. What's the angle now? Phi plus. Well, then 2 pi over t. And since it's t over 4, t over 4. So these two cancel, those two cancel, and you get pi over 2. How many degrees is pi over 2? 90 degrees. So it's wherever this one is plus 90 degrees. So I just moved this whole thing 90 degrees. But it rotated in what direction? Counterclockwise, right? Counterclockwise. Now let's assume your phi was 0 degrees. You would have been sitting exactly now on this imaginary axis. Okay, let's move one more. And we're going to, just want to see what I did over here. Yeah. Let's move, oh, you know what? Let's keep it there. What would happen at t equals t over 2? And what will happen at t equals t over 3? How much is this going to add? It's going to add 180 degrees. How much is this going to add? It's going to add 270 degrees. So this will lead to plus 180 degrees. This will lead you to plus 270 degrees. And every time this one just clicks over another 90 degrees. So this whole thing is rotating counterclockwise. So back to the question, what does e to the j omega t do to this whole thing? It rotates your phasor counterclockwise at a specific speed. What speed? That omega. And what is the omega determined by? Remember, omega equals 2 pi f. So whatever your supply frequency is, that's going to dictate how fast your phasor is going to rotate. So in reality, our phasor, or the component, or the real component of your complex, no, I need to check my words carefully here. Our phasor representation of our time function, in other words, the frequency domain, that part is standing still. We've taken a snapshot at time 0. But in reality, we're now, this thing is actually rotating because we've just ignored the E equals j omega t part in the equation. But we don't care the fact that it's rotating. Why not? Because all your phases in your circuit diagram are rotating at exactly the same speed because they're all connected to the same source. They're all connected to the same frequency or rotating at the same frequency. So all we are really interested in are the phase angles between the different vectors. I mean, if they rotate but they all stay the same angle, I don't really care about the speed. We want to know what is the phase angle difference between our vectors. Okay, so that you can go and look at a little bit. Your textbook, to show how this rotation thing works. Your textbook has got a figure. Let's quickly go back there to your textbook. So your textbook has this figure there to illustrate this rotational thing. So you can see it's rotating counterclockwise at that speed, omega, sorry. And then it's trying to show you that you can now take this rotational effect back to a sinusoid, but this doesn't work in a picture. So I'm going to show you a little video quickly. So what do you see here? There's a wheel, and our phasor is this arm. All right, that yellow arm. So this yellow arm is going to rotate. That's going to be our rotating phasor. And then the x component, the real component, dropped down onto a piece of paper. So what I need you to imagine here is you're going to see that this piece of paper is actually moving from the bottom to the topish, and this one is also going to slide from right to left towards the back. So in this case, at time 0, you'll see there this little red arrow says 2 pi, so it might as well have been at 0, right? Full rotation. So this is our time 0, or at 0 degrees. We only have a real component because my phasor's point is lying smack on the real axis. So cosine is 1. The sine wave, there you can see it says sine wave. You can't lack a read there where it says cosine wave. The sine wave is at 0 because my imaginary part is real, is 0. Now, as this thing rotates, it basically has a pen. Imagine that connected to a pen and that to a pen. And as this page slides past, this pen draws on this piece of paper. So let's see what happens. As it rotates, and I'm calculating the x and the y components, and those pieces of paper slides through, guess what do you get? A perfect sinusoid. And this is now that ej omega t part is doing the rotational bit. And we're just calculating that phasor at different points in time, but we're just actually interested in time 0. But this is just to show how that rotating, hey, you must go again, how the rotating waveform play, how the rotating phasor, the real part, gives me the cosine at the bottom. The imaginary part of this rotating phasor gives me the sine wave part. What part are we interested in? We're only interested in the real component. Now, so let's just pull this, all that we've done now, just pull this together, this whole moving from the time into the frequency domain. So let's assume we've got a voltage, Vt equals 10 cosine omega t minus 60 degrees volts. All right, so that's our time domain. And then we convert this into the phasor or the frequency domain, where V is now equal 10 angle minus 60 degrees. But remember now volts, all right? And this is also going to be in volts. So the units stay. So remember what we hammered on in chapter 9.2 is that it has to be in a cosine. All right, it's a sin to work in a sine, so you have to convert the sin into a cosine function. Right. How would we draw this in the time domain? In the time domain, well, let's say 0, 30, 60, 90. I just want to get a peek, then this would have to go through there. Oh, I've really drawn this out. No. I don't have that much space. Sorry. I'll have to make this a little bit shorter. Right, and then there again. All right, so I want my peak over there. So the cosine is going to sit over there. Jinx, 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 something like this. Peaks there, so it has to go through there. Oh boy, so much for my famed cosine function. Anyway, something like that. All right, so there we've got 60 degrees. It's a minus, so this whole thing shifted by 60 degrees, and my amplitude there is 10 volts. All right, so that is our time function. What would it look like in the phasor domain? In the phasor domain, it's 10, but what's the angle now? It's minus 60. So it's going to sit, I know, at minus 60 degrees, and the length of this vector is 10. All right, so that's my real axis, that's my imaginary axis. Or you can look at it as your xy axis. And that's your 60 degrees. Not minus, just 60, but we're in the negative direction. Now remember, as we mentioned, that if you've got a sine function, sine omega t plus phi, that is cosine omega t plus phi and then minus 90 degrees. You have to put in that minus 90 degrees there to make sure that you convert the sine into a cosine function. All right, very, very important. Okay, next we're going to look at what happens when you differentiate or integrate a complex number. Now, why are we interested in differentiating or integrating? Remember, even in chapter 7 and 8 that we did when we worked with inductors and capacitors, the voltages and the currents, you had, for instance, that the inductive voltage, VL, equals L di dt. So we had to integrate. But a capacitor voltage is the integral of the current. So what we're busy aiming towards here is that we will have to, what happens when we solve circuits with inductors and capacitors in an AC circuit, there's going to be a differential and integrals in play in determining voltages and currents. So if we want to represent our circuit in a phasor domain, in the frequency domain, we need to know what is going to happen to our phasor when we differentiate or integrate it. So this is where this part comes in. So again, we're going to visit and see what happens in terms of EIR. So we've got a time function for a voltage, our time function, and then in terms of an EIR, the real part. And we're going to take the differential of this thing now. So if we differentiate, it becomes, a cosine becomes minus a sine. So I just want to write this that I don't have to redo something later. Minus omega, so that omega comes to the front, minus sine omega t plus phi. But now the problem with this one is, it is a sine, so we have to convert this into a cosine. Apart from converting the sine into a cosine, we also need to get rid of the minus. So I'm going to do two flies with one swat, and we're going to do a omega Vm cosine omega t plus phi. Okay, first get rid of the minus, so let's add 180 degrees. And then to convert the sine into a cosine, we subtract 90 degrees. So this then becomes omega Vm cosine omega t plus 9, the phi plus phi plus 90 degrees. Okay, let's convert this now and write it in that format. So this is the real part of omega Vm E. And now everything in the bracket needs to go upstairs. Eh? So it's J omega t plus phi plus 90 degrees. I hope you can still see this on the video. And we're going to break this up into its individual components, and I'm going to reshuffle it a little bit. Am I? Yes, I am. Okay. So, you know what? For the sake of space, I'm just going to do it over here. So I'm just going to take this and just break it up into its individual components. J omega t times E J phi times E J 90 degrees. Okay. Right. Now, what is this bit? So now look at what's the same here. Perhaps, you know what? Omega t plus phi. I'm going to change it again a little bit. Plus phi. I'm going to keep those two together because now we can see that, hey, wait a minute, I've got Vm. That little bit there is exactly what we had up here. This and this is the same. So it's our original equation. Okay. So what came in extra? This omega came in extra, and this EJ 90 degrees. Okay, what is this EJ 90 degrees? Let's say, but EJ 90, according to Euler's theorem now, equals cos of 90 plus J sine of 90 degrees. What do you see happening? What is this then? That is 0 plus this is J1. Oh, okay. So this EJ90 is nothing but a J. So we can, let's rewrite this little bit again, now with that bit of knowledge. So that known, this equals the real part, go away, of J omega. So that J, this part becomes a J. This J I move to the front in front of the omega, and then what is this thing? This is going to be V, the J phi component, and then E to the J omega t. All right. So remember that Vm E J phi. You know what? We should have kept it separate. I knew there was a reason why we had, but I just wanted to show you that it's the same as the top. So let's make this again I'm shunting you around. Sorry, guys. Omega t times e to the j phi. All right. So this combined gives me this, which is the original term, but the Vm and the ej phi, as we saw, that gives you the phasor V, and we take the ej omega t separate, and the j omega. Where does that come from? Well, the omega came from the differentiation. The j comes from the fact that ej90 is just a j. Okay, so back to our original differential is now the real part, j omega v e j omega t. So what happens when we differentiate in the time domain? What then happens in the phasor domain? You take your phasor, the original v, and you simply multiply it with a j omega. So how am I going to write this? I need a bit of space. So dv dt in the time domain translates in the phasor domain to a j omega v. You simply just multiply your v vector with phasor with a j omega. And what would be the integral? Well, if you multiply with j omega, what's going to happen when you integrate? You're going to divide by a j omega when you integrate. Integrate. All right. This j omega can also be written as v times 1 angle 90 degrees. Remember, where is j on your imaginary axis? It's just one j. J sits at 90 degrees. So I can just multiply that by 90 degrees. Where's the omega, silly? Sorry. Omega. That needs to stay there. The omega times 90 degrees. And this oak would be v over omega angle minus 90 degrees, because 1 over j is minus j, which is minus 90 degrees, and the omega stays below the line. Okay, so that's quite a mouthful. We're going to obviously practice this in and run this in with a couple of examples. On page 379 of your textbook, there's a couple of important differences that we've already actually touched on. Let me just quickly read through them. So the first is that, remember, your time function, that's an instantaneous value in the time domain, where your v is in a frequency domain. They're not the same thing. That we mentioned already. Then the second thing is that your v of t, this booty, is time dependent. Your v is not time dependent. It only has a magnitude and a phase angle. So that's not time dependent. And then v of t is always real. This thing is always real. It exists. If you put your fingers in the plug, it will shock you. It won't be an imaginary feeling. And that is why we have to write the real part of a vector format or a phasor component that has both magnitude and angle, which means you can break it up into a rectangular format. So they will always be in the phasor domain, a real and that sounds weird, and an imaginary component. All right, so that's on page 379. Okay, so that is a mouthful of theory. So maybe the textbook makes more sense than I did, but hopefully I've added some value to this as you just see it breaking down. Okay, let's do practice problem 9.4. Practice problem 9.4, they give us a sinusoid, and what they want us to do is to convert this into the phasor form or the frequency domain. Then the other practice problems and examples, I want you just go and work through. There's quite a few, 9.5, 9.6 and so on. And then they want you to convert from phasors back to time domain. Now we're gonna convert from time to phasor domain. Rarely, only in the homework. In the tests and exams, I'm not going to ask you to go from phasor back to the time domain. But if you can do the one, you can do the other. Okay. So this, I think we've done a few like this. 2 problems with this this first bit is the fact that there's a minus. We don't want a minus. And there's a sign. We don't want a sign. Now, why is this exercise important? When we're going to get later to chapter 9, when we solve circuits, chapter 10, 11, etc., etc., there's going to be a source in your circuit. That source will be a voltage source. And I'm going to give you that voltage source in a time domain. And I am going to give it to you as a sign so that I can check whether you remember to convert the sine into a cosine. Okay. So we need to get rid of two things, the minus and the sign. That's pretty much what we did just now. Hey. So this equals 14 cosine 5 of t minus 22. Now, am I going to add or am I going to subtract 180 degrees to get rid of the minus? Now first let's do the sine to cosine. So first I'm going to subtract 90 degrees so that I can get from sine to cosine. And now I'm going to decide whether I'm going to add or subtract 180. Now what is the rule? So something 180 degrees. What is the rule for the sum of these angles? They have to be within plus or minus 180 degrees. They have to be within plus or minus 180 degrees. Now with this minus 22 and the minus 90, you get minus 112. So you can't subtract 180 because then you're going to be beyond. So I have to add 180 degrees so that I bring my angle within that boundary. And now I'm too lazy. It's going to give you 68 degrees. Okay, so it's 14 cosine 5t plus 68 degrees volts. Okay, don't forget the units. Okay, and for the B1, they've got a current there equals, what is it? Minus cosine, minus 8 cosine 16t plus 15 degrees. So fortunately, it's already in a cosine, so that's fine. It's only the minus there. So that's going to be, oh, we're not in the phasor domain yet, Mugu. So that then, in the phasor domain, gives me that V equals, not an equal sign there, just the arrow, is going to be 14 angle 68 degrees volts. All right, now that's the answer that we're actually looking for, the phasor domain. Okay, back to this one. So it's 8. I need to get rid of the minus, so let's just write cosine 16t plus 15, and now I'm going to add or subtract 180. Well, if you add 180, you're going to end up with 195 degrees, which is outside of my boundary, so I have to subtract now 180 degrees, so that gives me 8 cosine 16t. 15 minus 180 really gives me minus 165 degrees. So in the phasor format, it's 8. So hence I equals 8 angle minus 165 degrees amps. Whoop-de-doo. Okay, now this is the long road. Hey, when you get a bit of practice in this, I would just go directly from this one to this one, because the 8 stays, and I know the 15 need to subtract minus 180, and I get to this. And go and test this on your calculator. Hey, if you were to write or type into your calculator minus chalky 8 angle minus 8 angle and then 15 degrees amps. Mathematically exactly the same thing. But go and punch in minus 8 angle minus 15 in your calculator and see what happens. It's going to spit out this. All right. Now perhaps on that note, calculators. I'm not allowed to tell you that a calculator that can do complex numbers is compulsory. But I am allowed to tell you that a calculator that can do complex numbers is highly recommended. Now there are a few, I've checked this morning, there are actually a few apps that you can download on your phone that can do complex number calculations. I haven't tested them and see how easy they work and whether they'll be able to do what we need to do, but that's an alternative, I suppose, if you don't have the calculator. But yeah, if you can get a hold of one, it'll be handy. Okay, that piece of chalk is finished. Alright, so that's on those practice problems. I want to do another one, practice problem 9-point-ish. So go and look at practice problem 9.5, example 9.6, practice problem 9.6, example 9.7, very important. Go and look at that one. Makes for a very nice short question in a test and exam. I'm going to do a similar one, which is practice problem 9.7. Now, practice problem 9.7 is the one where that whole integration or differentiation of a phasor exercise comes in. So what I want you, so our objective is we need to find what is the expression for v of t, and they give us this integral differential equation. We've got dv dt, you've got a v, you've got an integral of v equals some cosine function. Now, just imagine for a moment having to go and solve this in the time domain. While we don't like differentials, integrals, so you'd probably go and then differentiate right through so that I can get rid of the integral, which will leave you with a second order differential equation. And we know where that's going to lead right from chapter 8. Not a nice exercise, and then now we need to figure out what v of t is. But if we convert this now into our phasor domain, so remember what happens when you take the differential. So we're first going to write everything in the phasor domain. So it's v. What happens when you take the differential? It's j omega v, right, plus 5v plus 10, and now it's an integral, so it's going to be v divided by j omega equals, and now just double check, it's not, there's no minus, it's already in a cosine, so I can simply write 50 angle minus 30 degrees. Okay, so now we're left with, unfortunately, a little unknown here, and this is this omega. But wait a minute, remember, that's why I have to give you something in terms of a cosine, because this little 5, that is your omega value. Very important piece of information sitting there. Okay, so we know omega equals 5. So let's multiply this then out. So I've got omega, which is 5 times 2. So this is going to be j 10v plus 5v plus 10 divided by that 5 gives me a 2. So 10 divided by 5 is 2. But this 1 over j is a minus j. Okay, so we actually have here a minus j2v equals 50 angle minus 30 degrees. Now again, now you've got polar formats with a j, and you've got a rectangular format, sorry, and there's a polar format. So let's just get this all into one format. So what do we get now? There's a 5v over there, so there's one real part, and then there's a j10 minus j2, so it's plus j8. V must equal 50 angle minus 30 degrees. Right. So what is V then? V equals 50 angle minus 30 degrees divided by 5 plus j8. Now I'm going to leave this. Yeah, okay, perhaps I should do it one step. So if you're going to do this on paper and you don't have a complex calculator, good luck. But either way, so 50 angle minus 30 degrees. What you would now have to go and do with this 5 plus j8 is to convert it into polar format. So 5 squared plus 8 squared, and take the square root of that, and then you get a 9.434, and for the angle it's the tangent a tan of 8 over 5, and that will give you a 58 degrees. Or you can just punch it into your calculator and it'll spit out the answer if you do a shift convert or something. Right, that gives me a final answer of, now I divide the coefficients, I subtract the angles, so that gives me a 5.3 angle minus 88 degrees. That's where I would stop. Where are we now? Volts. That's where I would stop for this, but the textbook wants it in the time domain. So the textbook then actually goes one step further, and they go and write 5.3 cosine 5t, because the 5t doesn't change, minus 88 degrees volts. So there's the time, there's the time domain function, there's the phasor representation. I'm going to stop here, because what extra did you show me to go from this to this? Nothing. You just showed me that you can write cos 5t. I'm interested in whether you can get to this point. So the homework problems have got a lot of exercises where they just simply expect you to do a couple of complex calculations to draw this in. So it is absolutely critical that you get comfortable with your calculator or whatever you want to use to do complex calculations. If you can't do that, you won't be able to do EIR, quite frankly, because everything from here onwards for the rest of this course is going to be complex calculations. Okay, so that's in the time domain. Now there's just one or two things that I want to point out at this stage. So I've already pointed out that omega t, that's very important. Then what was the other thing? Now I remember. The j bit. Now this whole time we've used a j and a j and a j, but in calculus they taught you to use an I for when you use complex numbers. Why aren't we using an I? Because I is for current, right? So we can't use an I in this case. So we have to use a J. And the other important thing is we don't write 5J. And I know in calculus we used to write 5I, and you'll see that usually they typically still do that. But we always write it in terms of J5, or 2 plus J5. Put the J in the front when you're doing the complex numbers. Okay, so that was just the other thing I was thinking about. All right, so now you can see by doing this difficult time domain calculation, converting it into the frequency domain, you get to the answer much quicker. Why the dVdt? Where do you get a dVdt? That's when you calculate capacitor current. Where do you get integral of V of t? Is when you calculate inductor current. So you can almost see this as an expression with a current times a admittance and a voltage times an admittance, so that you can get a bunch of current expressions over here to get the voltage. So finally, you then get the voltage that they were looking for. They asked it for V of t, so we give it in terms of time. In the test, I will just ask you what is V in phasor format, and you'll stop your answer right there. Okay, in the next little short part, we're going to now further apply this principle, this integral differential, on chapter 9.4. Chapter 9.4 is going to be very short. Obviously, I'm going to go through what the textbook does, but perhaps with a bit of a shortened version. So what now that we can convert the time domain into the phasor domain, we want to apply that principle and the whole integral differential principle to, I call it the ohmic laws for the inductor, the capacitor, and the resistor. So we're going to see how V equals IR, VL, di dt, all those convert into the phasor domain. So we're going to take them one by one. So they give us a current of a certain amplitude, and the textbook just gives a plus phi, but I'm going to put a plus 30 degree there so that we can draw the pictures nice. Okay, so for a resistor, we know that applying the convention, if you have the current there flying, then our convention says the V must have a plus minus, right? Now the equation, V equals IR. Convert that into the phasor domain. I get V equals the I becomes capital I with a streepje or just bold printed times R. Let's draw this now in a vector format. All right. So there's my V. No, sorry. They've given us the I. So let's start with, they give us the I. All right, so there's my vector I. How do I get to V? I simply multiplied with R. Now, R is just a scalar. So I'm literally just scaling I by a factor of R to get the volts. So is the angle going to change? The angle is not going to change. I'm simply taking that vector. It's still going to point in the same direction, hopefully, and I get V. All right, so those two phases are in phase, those two vectors. So remember when we talked about beginning of chapter 9.2, we talked about those sinusoids either being in phase or one can be leading or the one can be lagging in chapter 9.2. So in this case, the fact that those two phases are sitting right on top of each other, that means that you've got two sinusoids exactly in phase. They're simply scaled by a factor of R. So that R will just be multiplied with Im to get the Vm value. All right, so that is it for a resistor. Yeah, perhaps we can also write this as Im angle 30 degrees times R. All right, so no change in the angle there. Okay, so that's it for a resistor. So very important rule for a resistor. The voltage and current is always in phase. For a resistor, the voltage and the current is always in phase. Okay, let's go to the inductor. Now there's some space left. So for an inductor, so now we've got this. And again, the current is in that direction and the convention says, again, plus minus. But the equation then is that V of L equals L di dt. Okay, now let's convert this into the phasor domain. So V must then equal the L stays there. What happens to, there's a di dt. What happens again when you differentiate and you go to the phasor domain? You have to multiply with a j omega. So we're going to multiply with j omega times the I. All right, because it's I that we're differentiating. All right, so let's rewrite this a little bit. So it's j omega L times I. Okay, so what have we done? So again, where's our current is still on the same spot there. Let's redraw it for this. We should have drawn it all of them in the same. I think it'll still work. I'm going to keep this picture there. So the current stays there. So this is VR. What am I doing with this I to get to V? There's a scaling factor, L, which is a scalar, but there's this j omega. So this is also, remember, what is a j? It's got an angle of 90 degrees. So we can rewrite this as omega L times the I. Let's do it like this. Omega L angle 90 degrees. So we've converted basically from a polar format, from a rectangular format to a polar format, and then still multiplied with I. So what am I doing with this I vector? I am multiplying it with omega L, a scaling factor, but also adding 90 degrees to it. Okay, so where's that going to sit? It will have to sit over there. VL will then have to sit over there. All right, I hope you can still see that one. So what is the rule then for an inductor? For an inductor, the current always lags the voltage by 90 degrees. Now I'm specifically saying the current relative to the voltage. We're always going to talk about current relative to voltage. Again, it's an electrical engineering thing. The textbook might say the voltage leads the current. That's not electrical. Electrical will say the current lags the voltage by 90 degrees. Current lags, because how come? If you're going to sit and look at from this perspective, first the voltage will come, then the current will come. So current lags voltage by 90 degrees. Right, then for a capacitor, do you think we still have some space here for the cap? Yeah, let's do the cap here. I'm going to squeeze it in here at the bottom. So for the cap, we've got the same story, plus minus V, the current that's flowing over there. And if we write the time domain equation, V of C equals 1 over C, the integral now of I dt. All right. So if we convert that now into the phasor domain, it's 1 over C. The integral is 1 over J omega, and then times my I vector. All right, so this we can write then as 1 over J omega C times I. Let's also put this in terms of an angle. Here at the bottom, let me see how you can still see there. So this is going to be 1 over omega C. The J below the line becomes a minus J. So that's a minus 90 degrees. Minus 90 degrees. And then still the I. Okay. So what do I have to do with the current to get the voltage? I forgot the voltage there. So V equals, did I put it there? Yeah, there it is for the inductor. So there's my VC. Let's call this my VL, and this my VR. Right, there's the VL. Okay, so what do I do with the current to get to VC? Well, I multiply it by a scaling factor again, which in this case is 1 over omega C. So it's going to get, well, depends on the capacitor, hey? 1 over C, but the angle again, now I'm multiplying with minus 90 degrees. So wherever the current is, minus 90 degrees. There's my capacitor voltage at minus 90 degrees. So what's the rule for a capacitor? The current leads the voltage by 90 degrees. Okay, so let's go back. A resistor, the current is in phase with the voltage. For an inductor, the current lags the voltage by 90 degrees, and for a capacitor, the current leads the voltage by 90 degrees. Right, so those three important rules. Let's do, before I get to, you know what? I almost want to go over to chapter 9.5 already, but we'll leave that for the next one. I want to do a quick practice problem with you, just so that we can apply this. All right, so please go and study these principles. This is going to come back over and over again, these rules. But yeah, I think chapter 9.5 will help us to just fix that in a bit. Okay, I'm quickly going to draw practice problem 9.8 on the board. Okay, now the textbook for practice problem 9.8, they actually don't give you a circuit diagram. They just tell you that they apply this voltage across a 15 microfarad capacitor. But I like to put it in a circuit format, so you've got a voltage source, sinusoidal. So that's why you see they've got a sinusoidal thingy there. And just a reference polarity, because remember, sinusoid, the plus and the minus, that's alternating current meaning alternating polarity. but we just need a reference polarity. So they're the plus minus. Then that's applied across a capacitor, and what they want us to do is to calculate this current flowing through the 50 microfarad capacitor. So what we're going to do, we're going to go from time domain to frequency domain, and then from the frequency domain back to the time domain, because they want the current in the time domain. Okay, so first let's convert that voltage. So V, let's convert that into the phasor domain, equals, first thing that you see is it's a sin. Alright, so we need to convert it into a cosine. So we get 25 cosine 100t minus, now remember, to get from a sine to a cosine, we need to subtract 90 degrees. 15 minus 90 gives me a minus 105. Is that within the plus minus 180? Yes, it is. So we can just say it's minus 105 degrees. Okay, so you can go and write this as minus 15 minus 90, but I mean, you should know that by now. Okay, so this is still in volts, and right, so we've converted into maybe we shouldn't have written that one yet. Hey, first into a cosine, and now we can say V equals 25 angle minus 105 degrees. Now in practice, I'm not going to write this step. I'm just going to go immediately from this and see that it's a sine, and I need to subtract 90, and I get my minus 105 and write out my phasor. Okay, so now what the voltage is. Then once I've got the voltage, now we know from that what we did just now, when it's a capacitor, we saw that it's 1 over j omega c, and then times the where am I now? The current. Yeah, I, like this. Right, so that was our original equation. So do we know what V I have? Check. We've got that now. Omega, do we know what the omega is? Yes, 100. All right, so we know omega. Check. Capacitance, check. It's only the current that we don't know. So from this we go that I must then equal V times J omega C. All right, if we take that to the, is it really this? It's really that simple. Okay, so we've got, let me just stand this side. So we've got 25 angle minus 105 degrees multiplied by, and now I'm going to take the J, which is a 90 degrees. So I'm going to add that. So then the omega is 100, chalky, right, 100 times C is 50 microfarad, 50 times 10 to the minus 6 angle, and it's a plus J, so it's plus 90 degrees. Okay, so you chuck that into your calculator and you get a 0.125 angle minus 105 plus, no, minus 15 degrees. Now we're just back to where we started. Okay, but anyway, so this is now still in volts, but this is now the phasor domain, and we want this in the time domain. Okay, and this is now where for me this simple bit comes in. So I of t, now you just write the whole thing, 0.125, and cosine 100t minus 15 degrees amps. Now the textbook, hopefully, the textbook didn't do that. Then I would be really just disappointed. They did. Oh, I can't believe it. So then the textbook actually went from a cosine back to a sine, because this is a sine. No, you don't do that. Okay, just stick to cosine, which means you might as well just stick to this. So this is what I'm going to expect from you. Okay, that is it for chapter 9.4 actually, all short and sweet. Chapter 9.5 actually builds on chapter 9.4. So in the next lecture, which is going to be actually lecture 13 according to the schedule, because now we've done 11 and 12 combined. In lecture 13, we're going to cover both chapters 9.5. 9.6 is for yourself. That you'll see we don't need to cover that. And then 9.7. So chapters 9.5 and 9.7 in lecture 13, which will be the next one. Okay, a lot said, a lot of theory and concepts to get used to in this lecture. So yeah, remember, go through the textbook, go through the lecture. I know we didn't do a lot of examples now, but you're going to see once we get to chapter 9.7 and then in chapter 10, we're just going to drill in all these concepts. Okay, so hang on with the theory. The practice with this will come, right? But you need to just assimilate kind of what we did now and have it in the back of your heads so that you can bring it to the front when you need it. Okay, so don't put it back too far. I'll see you in lecture 13. Thank you. Cheers. Bye-bye.